All right, I think we're ready. We're going to do a little bit more on beams today. So we've got several, actually, there's a couple more topics, and the rest of the middle section of this course really kind of just keeps building on these idea of beams. And remember, the frames and machines have at least one beam in them. That's what separates them from being a truss. And so most all of the content in the second third of the quarter, so the middle, is somehow related to beams one way or another. It's really flexural stress, bending stress, things like that. Things are bending now, and usually that thing that's bending is a beam. Before we actually do more just about beams, remember last time we were calculating the bending stress in a beam. What I want to do is I've had several questions about a particular web work problem. This one, that, it's a frame. It has a cable in it, so that does complicate it a little bit. Well, not complicate. It makes it different than, just bolted metal pieces. So it makes it different. And it does have a slot, so that's something that we haven't done a lot of. And so it'd be good to go and work over this one. This one also has two pin supports, one at A and one at G, so that makes it also a little bit different. You could easily get lost in this one trying to solve a piece that you don't have all the information for, or maybe there's too many unknowns. There is, I don't want to call it a trick to this one. There's a couple of things though that make this one much simpler. One of them I don't think we've specifically talked about though, so let's copy this guy and work on it. Let's see, that looks good. Put him over here. There we are. All right. So these are the numbers that I have. You would have different sets of numbers in here, but it'll be similar. First thing I want to do, though, is I notice that H is in feet and all the other A, B, C, D are in inches. So I'm going to change H over into inches also before I make a mistake with that. So it's 34.8 inches. So let's just change that to that, just so I don't forget later on and have a 2.9 in there or something like that. All right, so this one has a couple of little things that are going to make it have some issues. It even points out one of them. The distance AG is deliberately not provided. So that's the distance between point A and point G, which would be one thing that could be useful. So let's kind of remove this support here and here and draw in some external reactions just to see what it's going to look like. And I'm just putting these in the positive directions. I know they can't all be positive, but let's just look and see. And I do have a value for F. For me, it's 210 pounds. So looking at this, you can already see there are four unknowns, AX, AY, GX, GY. So that means that I'm not going to be able to solve for all of them with my three equilibrium equations for the whole frame. Normally, I would say that I could at least get GY and AY by doing summation of moments, except in this case, that thing I highlighted is that there is no given distance between A and G, so I can't do moments about A and have GY times some moment arm because I don't know what that moment arm is, and there's not enough geometry here for me to calculate that. I might be able to calculate it using the DEB triangle type thing because I do know the height of that triangle, but that's probably not the best thing to do. I probably could figure out, I don't know if I could get close exact or not, because it's not, doesn't look like it would be quite what I need to do. And so if you get into a situation on an exam in this course where you've got something like this, then it's probably telling you that there is some other thing that is going to help you out. And so usually for a frame or a machine, what that means is go ahead and take the frame apart and look at the individual pieces. So that's what I would do next. I would draw ABC. So something like this. Here's A, B. I want to do a certain thing at B. C. At A, I've already put AX and AY, so I'll put those on here. At C, now you have to pay attention to where that F equals 210 pound external force is loaded. It's actually loaded on member CDE. So if you see it's actually pointing or pushing on that member. It's not actually pushing on this member. So I don't put the 210 pounds on here, but C is a slot, and there's some sort of roller or pin that's sliding in that slot up and down. We're assuming that that slot is frictionless and that the reaction is only perpendicular to that slot. So I will put something like this. I'll just call it C, the force in C. I don't need a CX and CY because I do know that the reaction is perpendicular to the slot. And at B, this is the thing I don't think we've specifically talked about. Again, we're doing frictionless pulleys. This problem doesn't actually say that the pulley is frictionless, but for this course, we're going to assume that the pulleys are frictionless. So that means that the tension all the way around this pulley, in the cable tension, is constant. It's not any different on one side of the pulley than it is on the other side of the pulley. It's just in a different direction. And when you have this sort of situation, one thing you can do is I don't have to draw the pulley in here. Instead, I can think of the pin, the little axle or the shaft that the pulley is mounted on. There's got to be some sort of axle shaft type thing there that the pulley spins on. And I can think about that as what I've drawn the picture of here. So maybe I've drawn the pin at B, or maybe the hole that the pin is in, either one. And I can draw the reactions of whatever's going on with this pulley directly on that pin. And as long as it's frictionless, then those reactions are just the tension in the cable. I'm just going to call it T. I don't know what it is, but I'm going to call it T. And so instead of putting the tension in the cable coming off of the pulley at some point, then I can just take those same cable forces, T, and put them directly on the pin that is supporting the pulley. And that it makes it a little bit simpler. The bottom, the horizontal T that I've drawn, this one, it is not so hard to figure out where it would be applied. It's just going to be half of the diameter of the pulley. The other one is also half of the diameter of the pulley, but you don't know, is it here or here? You don't know exactly where it's coming off of that pulley. You'd have to do a lot of geometry to calculate that. So instead of dealing with that, I'm just going to remove the pulley entirely, make my free body just the frame member itself, not the pulley, and replace the pulley with the cable forces that were on the pulley. And I can put them right on the pin at B. So that helps me a little bit because it helps me figure out where some of these forces, I can locate them better. So now I can say for sure that this distance is, well, the way they've got it laid out here, C would be from A to the bottom of the pulley. And then I've got the diameter of the pulley as 3 inches. So this is 2, C is 2. 2 plus 1.5, so 3.5 inches. And then this is going to be 34, H for me is 34.8 inches. I've just converted that. Minus 3.5, so 31.3 inches here. Okay, now I can't solve it. I have too many unknowns. I have C, T, AX, and AY. So I still have 4 unknowns, but that is what I would do first. I would probably, if I wasn't sure what to do next, I would probably just draw the next free body diagram. In reality, what I would do, I guess, is I would look at this and see, is there any place I can do some kind of summation of moments or forces in a certain direction to get any values, but I don't know anything. These are all variables, so there's nothing here I can solve for other than more equations. I can solve for more equations. So I would probably go and see that, well, I don't know any of this stuff, so I'm going to draw the next piece. Okay, I've got G. Well, I'm going to put my dimensions over there. Let's put G over on this side. E, somewhere in here. And then D is up here. And C is over here. GX and GY, I just put those as unknowns, and I put them in the positive direction. E is where the cable comes back around. So I can know that there's just some force T. I am making the assumption that I don't think is specifically stated in this problem that the cable on the bottom is actually horizontal. It's not at some angle. It looks that way, and I don't have any indication that it's not that way. There's no slope on it. There's no dimensions that would make me think that it's not horizontal. So I am assuming that this bottom T that I've drawn is actually horizontal. Up here, I do have information that tells me about the slope of this, and these are the same part of the cable. I've just cut it in two different places, so they have the same angle. C, I've already shown C on the first free body diagram I drew, so I have to draw the opposite version, same magnitude on this one. And I do have that external load here that's pushing on the little end of this right angle piece. And it's 210 pounds. So at least I know one thing on this one. It has 4 unknowns also. So I can't solve for everything, at least not at once. So what I would do next is I would look, first of all, the problem is asking for the tension in the rope and the force at point C. So that kind of gives me a little clue that I'm not necessarily interested in solving for GX, GY, AX, AY. They're not part of the problem statement anyway. So maybe if I write equations that don't include GX, GY, AX, AY, then that'll get me somewhere. I also noticed that I have 4 values of T. They're all the same value. 2 of them are on one free body diagram and 2 on the other free body diagram, but they're all the same magnitude. So that could be useful. Even though there's 4 arrows, it's all the same number. Same thing with C. There's 2 C arrows, opposite directions, but same magnitude. So I have fewer unknowns than I think I do. In fact, I have C, T, so that's 2 unknowns. AX, AY, that's another 2, that's 4. GX and GY, that's another 2, that's 6. So I have 6 unknowns on these 2 free body diagrams. Each one of these free body diagrams will allow me to write 3 equilibrium equations, X, Y, and a moment equation. So I have 6 equations, 6 unknowns, so I should be able to solve for this. So that's one thing you could do. You could write your 6 equations, put them into a simultaneous equation solver, and solve them that way. We're actually going to do a different thing, though. Since I'm not interested in AX, AY, GX, and GY, I am going to write moments about A and moments about G and end up with 2 equations that have 2 unknowns, C and T, the 2 I'm looking for. So let's see. We need a little bit of room to put our writings. All right, so looking at the first free body diagram I drew, summation of moments about A. I'm going to do clockwise positive just because that's what I want to do. You know what? I need to know a little bit about this angle that T is at. I have this information. A is 3. B is 2, so I can figure out what the hypotenuse is. Let's see. A squared plus b squared is equal to c squared, which is 3.606. Okay, now we can do a little bit more. So I've got ax and ay. I'm doing moments about a, so neither one of those enter this equation, so I don't have to worry with those. I have t, the horizontal t, times 3.5 inches, creating a clockwise moment. I have the x component of the angled t, also creating a clockwise moment, so plus t, only the x component though, so 2 over 3.606 times, that also has a 3.5 inch moment arm, plus, the way I drew it anyway, c has a 34.8 inch moment arm. Those have to add to 0. I can't solve that. There are two unknowns, but I only have two unknowns. I can simplify it a little bit. So I've got t times 3.5 and t times all this other stuff. So 2 times 3.5 divided by 3.606 plus 3.5. So I've got 5.44 times t plus 34.8 times c equals 0. So that's the equation that I would end up with if I kind of simplify it. All right, now I go to the other free body diagram. Oh, I know this dimension is c, which for me is 2 inches. And then this one is, what is this, 34.8 minus 2, so 32.8. Okay, that's all I need for that. So second free body diagram, summation of moments about G. I'll do clockwise positive again. Even all of those are, almost all of these are counterclockwise. So I've got negative t times 2 inches minus the x component of t that's angled, so minus t times the x component is 2 over 3.606. It has a moment arm of the 34.8 minus c times 34.8 plus 210 pounds times 34.8 inches equals 0. So this one I can combine the t there. So let's see what that is. 2 times 34.8 divided by 3.606. That's a negative one, so let's subtract off 2. I think it's, let's see, is that right? 30, wait, hold on, let me make sure. 34.8 from G to up there, okay. 2 times 34.8 divided by 3.606. Oh, those are both negative, so let's actually add those together, but they're negative. Negative 21.3, we'll call it 3, times t. Negative, there's only one c, so negative c times 34, oh, you know, I wrote it the other way, 34.8 times c. This one I do have 210 times 34.8, so 7308 inch-pounds. I'm going to move that to the other side of the equal sign, so it actually becomes negative 7308 inch-pounds. And if I look at my two simplified equations, I see that there's a really convenient part in here that I've got positive 34.8 times c in equation 1 and negative 34.8 times c in equation 2. So if I add these two equations together, then 34.8 plus negative 34.8 will be 0, and I will have eliminated the C variable, and I'll only have T. So I'm going to add these two equations. So I've got a negative 21.3 added to a positive 5.44 T, which gives me negative 15.86 times T. The 34 plus the negative 34 is 0. So equals 0 plus negative 3708, so negative 7308 inch-pounds. And therefore, T turns out positive because of the two negative signs. 7308 divided by 15.86, 460.78 pounds. And then it's just a simple matter of picking one of my equations. Might as well do that top equation and plugging this value in for T. So 460.78 times 5.44 divided by 34.8. C is that would be a negative value. I didn't write that down, but that's all I did. Is I took this value for T and plugged it in right there and solved that equation to find C. That's all I did. All right. So hopefully 470.6 or 460.78 and negative 72.03 are the values for T and C. So let's see. 460.78. This one needs units in it. Negative 72.03. Whoops, didn't put negative. Negative 72.03, also pounds. Let's see. Oh, log in. And we are right. We're correct. So would this be an exam problem? This would be a really tough exam problem just because what you actually end up doing is not hard. You know, writing two moment equations and adding them together, that's not very difficult mathematically. It's getting to the point of realizing that's what you need to do. That's the hard part on this one. So it could definitely be time consuming if it were an exam problem. So I don't think something quite like this is going to show up on an exam in this course just because it takes too long to figure it out. There's too many little bits that you would have to get through because most people probably would try to find AX or AY and GY first, and you'd spend a little bit of time trying to figure out a distance between A and G, and so that there's no good way to do that. Then if you start writing maybe you realize to break it apart and start writing the individual equations for each piece of the part of the frame. And so there's just a lot of little things that would, unless you just immediately saw what to do, it's going to take a long time to just work your way through it. The actual stuff to do, not very complicated at all. And that's how most of this class is. It's not mathematically intensive. It's algebra at most. Maybe a tiny bit of calculus every now and then. But the real part of this is drawing correct free body diagrams and then just systematically going through and applying your equilibrium equations to those free body diagrams to figure out what equations you have to work with, which works fine on homework, but not so well on an exam because of the time constraint. All right, anyway, I had several questions about this particular problem, so I thought I would address them. So that's what I did here. Here, what we're going to do now is go on to another web work problem. This one is more along, this is an optional one, so it's optional 2, problem 5. This is more like what we've been doing yesterday, where we did the internal shear and bending moments. The difference here is we want to actually develop equations for this internal shear and internal bending moment for different sections of this beam. Remember I said that some of the problem with figuring out flexural stress in a beam the way we did it last time was that you don't know, or it's not easy to know, that you have picked the slice where the bending moment is highest. You can kind of look at the beam and maybe pick out some points that look like they would have a high bending moment, but you don't know that. And so this is a way. It's still cumbersome. It's not going to be the final way that we do this, but this is a way to develop equations for each section of the beam. So you kind of see how it's got these different intervals of the beam, corresponding to this interval, this one, and this end over here, and developing equations or expressions for each one of those intervals. And then you could plot them and find out where the maximum bending moment is, maximum shear force also. So you could do it that way. But you could also really realize that a beam could have a lot of different intervals, and it could be very cumbersome to do that. So there will be exam problems, or maybe a exam problem that uses this type of approach like we did last time, where it's this approach, except I specifically tell you the section to look in, instead of you having to go figure out which section is the important section. All right, so what this is, I've got a sort of simply supported beam with a cantilevered section. So it's got a pin and a roller, so that makes it simply supported. And then there's this little section A over here that's cantilevered. Cantilevered means that it's not supported on one end, and all of the support for that piece is on the other end. And so it's kind of just hanging out in air. I've got some force values, some distances, and a bunch of blanks. So let's copy this so that we can get it over into OneNote. And let's work on it over here. Now, it is telling me, let's see if I can make this, maybe it's just, I don't have a good color that's actually bright white here. I've got maybe a cream color. Oh well. All right. Let's replace all of these dimensions with what they actually are. So I've got 2.7. These are feet. C, B, and A. Let's plug those in. A is 2.3 feet. B, 2 feet. C, 5.1 feet. And then I already put D in there. F1 is 2,190 pounds. W, so this is the distributed loads value. W, 750 pounds per foot. And then the last point load is 1,740 pounds. And at A, I've got a roller. At B, I've got a pin. So I'm going to put BX, which is just 0. I can look at it and see that there are no other external forces that are angled in the X direction at all. So I know that BX is 0. BY, I don't know its value. In fact, that's the first thing it's asking me. AY. Well, they call them RA and RB. So that's what I've called AY and BY. All right, so that's the first thing, is we need to go in and figure out the reactions at the pin and roller. Well, before we do that, let's go ahead and get this distributed load. Let's create a lumped version of it so that we can work with moment equations and things like that. So it's 750 pounds per foot. Oh, I forgot about the low battery on my calculator. Uh-oh. Well, if it quits, we'll have to do something. Figure it out. 750 pounds per foot times 5.1 feet, 3,825 pounds. I'll put that as a... I like drawing these in some odd color other than red, because I don't want them confusing myself later that this is another point load. It's just the lumped version of the distributed load. So it was 3,825 pounds. And we would put it, since this this is an evenly distributed load, so it just looks like a rectangle. I would put it in the center, where the centroid would be. 5.1 divided by 2, 2.55 feet. All right. So why don't we do moments about point A, where the origin is. So right there, this will be point B. So summation moments about point A. We have the 2,190 pounds actually creates a counterclockwise, so minus 2190. Again, I'm going to leave the pounds and feet off just to save a little room on the page and it doesn't get all squished together. I have made sure that these are all compatible units. You know, they're all pounds and they're all feet. I don't have any newtons or inches or anything that's going to mix it up. So 2.3 plus 3,825 times 2 plus 2.55, so 4.55 feet. Plus, I can't forget that point load at the end of the distributed load, so plus 1,740 times, looks like that's going to be 7.1 feet. And then I drew BY pointing up, so minus BY times 5.1 plus 2 plus 2.7, 9.8 feet. Okay. The only unknown, oh, that equals 0. The only unknown in there is BY. So we should be able to find a value for BY. Let's see. So I've got negative 2190 times 2.3 plus 3825 times 4.55 plus 1740 times 7.1 divided by, so move BY over to the other side of the equal sign, makes it positive, and then divide by 9.8. 2,522.5 pounds. Then you could do summation of forces in the y direction equals 0. I have negative 2190 plus AY minus 3825 minus 1740 plus 2522.5, that's BY, equals 0. And I get a value for AY. So let's see, negative 2190 minus 3825 minus 1740 plus 2522.5. I move that to the other side. It's a negative. It's negative 5232. So I move that over. It becomes positive 5232.5 pounds. So I've got AY and BY, hopefully. At this point, since this is a web work problem, I'm going to check those and make sure that we are correct on that. So let's see, what was it? AY was the 5232.5 and BY was the 2522.5. And we got the, all right, so we are right on those. Good. Okay. Now here's where we start doing the equation, what they call them expressions, develop expressions that describe the shearing forces and bending moments in the beam in these different intervals. So what we do here is we look at the interval. So the first interval is negative 2.3 to 0 in the x direction. So that's this little piece of the beam. That's the first interval. So I will go in and cut in the middle of that guy. And in this case, I'll draw the left-hand side because it's a really short piece, so I'll draw that. So they just call this negative 2.3 to 0. So that piece has 2,190 pounds on it. It has a shear force here and a bending moment here. This distance is, well, actually, It's not X. X starts right here. So I'm assuming they want us to follow that. We might have to figure out exactly what they want there. So it's actually, let's see, what's the best way to do this? This distance is 2.3 feet, and I guess this distance here would be a negative X. I think that's the best way to do this. I think we'll find out soon. All right, so V, here's V. That one's easy. Let's do that one first. So to calculate V, we do summation of forces in the y direction equals 0 for this, just this little piece of the beam. And I've got negative 2190 pounds minus V equals 0. Therefore, V equals negative 2190 pounds. Now, I wonder, let's see, if it tells me anything about signs. It doesn't give me any instruction on directions, or if I need to put negative signs or positive signs on here. We're going to put that it's a negative 200 or 2,190 pounds all in this entire section. It doesn't depend on where we slice this one. If I, sliced it here or here, those would give me the same equation when I do forces in y direction. And in anywhere in this first little interval, the shear force is just negative 2,190 pounds. So we should be able to, well, actually we should look right there. Yeah, there it is right there. So negative 2190. It already has the units on there. So we should have another check. Okay. The bending moment. Oh. So here, let's do summation of moments about where we cut our little free body diagram. And that has to equal 0. So we have negative, the way I drew it, I said clockwise was positive. So negative 2190 pounds times this distance is going to be 2.3 feet minus or plus negative X. I wonder how I need to, I think I will need to add negative X to this because I want to just get this distance here for the moment arm. So I'm thinking that I'm going to have to write it this way. Okay. Well, it's 2.3 minus, well, no, I can just do 2.3 minus, well, plus negative X is the same as minus X. Plus negative X makes it a little bit more sensible to me because X starts right here, according to the picture. Okay. So that would be the moment created by the point load. Shear force doesn't create a moment on the plane that I'm cut at, so that doesn't do. M, I don't have to worry about a moment arm. I just need to worry about if I put it in as plus M or minus M. This M is counterclockwise. I said that said that moments were clockwise positive, so this would just be minus M equals 0. Therefore, I can move M to the other side. M equals 2190. So 2190 times 2.3, 5,037. That would be foot-pounds plus X. Well, 2190X. I don't know if WebWork is going to want us to put units on this. In fact, I don't think they will, but let's see. Well, so they wrote the equation without units, and they left it as more like this over here. except they have the negative here and plus x, 2.3 plus x, because x is negative. So I guess that's what it is. This is plus the x distance, but when you put in the value for x, it's actually like -1 or -2 or -2.3 or anything like that. So x itself is negative. So we don't need a negative sign in the equation because the value of x is going to be negative. So that's what's going on there. So we could just leave it like this and just move m over here. I wonder if it'll take it this way. Let's see. Now I'm just curious. 5037 plus 2190 times x. Oh, 2190 times x. Let's see if if it likes that or not. No, it doesn't like that. So it does seem to be that web work wants things kind of collected together on terms. Just so when you're solving this one, or one like this one, you might want to know that. So 2190, or negative 2190 is what they want, right? Did I put my negative? I didn't put my negative sign. That's why it's... I didn't put my negative sign on there. So that might be why it is complaining. Now I want to try it. Well, still doesn't like it. So I think it does matter if it is collected on terms or not, because these two things should be, equivalent, but WebWork doesn't recognize that they are. So when you're working on these in WebWork anyway, it does look like it matters if you collect on terms or not. Just so you know. Yeah. So I think that's a function of WebWork. So it will care when you're going and doing the homework, because there's some like this in homework 12, I believe it is. It does seem to care if you collect on terms or not. So it wants you to collect, with the parentheses. All right, well, that's good to know. All right, let's go to the next interval. So the next interval in our beam, they have it labeled as from x equals 0 to 2 feet. So it's avoiding the exact points where like x equals 0. Those can be a little bit confusing because it depends on if you're approaching it from the left or the right hand side sometimes, because those can be oh, did I put the wrong number in? Maybe I put the wrong number in. You're saying that would be interesting. Maybe I might have typed it wrong, because that would be good to know. Okay, yeah, I typed the wrong. It's equivalent to the one I just submitted. So I typed the 3 and 7 backwards, maybe. I don't know what I was typing backwards, but I was typing the wrong number for the 5037. I have it in my calculator as 5037, but for whatever reason, I didn't type it in that way. So it doesn't matter if you collect on terms. Good. All right. So what I was saying is it is avoiding some of the like supporting points where a point load is applied, where a distributed load starts or ends, because those when we get to drawing the free or the shear and bending diagrams, those will it'll be more obvious that they're at that individual point. It matters which way you're looking at it, from the left or from the right. It can have different values. So that's why this problem is there's no x equals 0 on here, because that's going to be kind of a disjointed value. All right, so let's look at the next section. Now, we have to be careful. The next section is not this up to that arrow, so don't, you might even want to erase this thing now that we're done with it. so it doesn't confuse you. It's just that little section. So I'm going to do the same thing. I'm going to come in there, chop it up right there, and draw that free body diagram. We'll put it down here. So this one has the 2190. It has AY, which 5232.5 internal shear, internal bending moment. Okay, and it has 2.3 feet here, and it has X here, because it depends on where we actually cut it open at. Let's do the easiest one first. So for the shear force in this section, so this is from 0 to 2 feet. Summation of forces in the y direction equals 0. And we have negative 2190 pounds plus 5232.5 minus V equals 0. So again, this one is going to be a constant. So negative 2190 plus 5232.5. V going to the other side makes V positive. So V is 3042.5 pounds. Okay, so again, it's constant. It doesn't depend on X at all. So it's just anywhere in this section from the point load where the reaction is to the start of the distributed load, the shear force is a constant 3042 pounds, hopefully. Yes. Okay. The bending moment, M. Summation of moments about that little cut surface that we made for our free body diagram. We've got 21, so negative 2190 pounds. Its moment arm is X plus 2.3 feet. Plus 5232.5 times X is its moment arm. Minus M, so I'm just going to move that to the other side and say equals M. And now I've got a little bit more, I could probably write the equation in just like this. There is, I can combine the X's. I could expand it out, combine the X's, but let's just try to type it in this way. So if I can get all the numbers in right. So negative 2190 times X plus 2.3 plus 5232.5 times X. 5232.5 times X. See if it likes that. It did. So we can keep the equation, well, they have it the same way also. Just the other one first. Okay, and so what we can begin to do with these is each one of these little intervals, we could plot these equations versus X and have a graph of the shear and bending moment all throughout our beam, assuming we write an expression for each interval of the beam. That's similar to what we're going to do later. Maybe we can do that later today. It just depends on timing. But we will do it either today or Monday. All right, so let's go to our next interval. So our next interval would start where this one left off and go to here. So we would cut through there. This one we're going to have to deal with the distributed load. So let's draw what we have here. So I've got the 2190 pounds. I've leaving off units a lot. I think this was 750 pounds per foot. Yeah. Here's the shear force. Here's the bending moment. Okay. Oh, and we have 2.3 feet, 2 feet, and X. So X does have to be measured from right here according to our free body diagram that puts the origin right there. Okay. So let's see what we can figure out with this. We got V. Summation of forces in the y direction equals 0. Negative 2190 plus 5232.5 minus, now here's this distributed load. We need to figure out the concentrated value of this distributed load. So 750, the units might help us here, so pounds per foot times how many feet do we have? So we have X minus 2 feet of this distributed load. Minus V, so I'll move V to the other side just to have equals V. And we'll go ahead and put the 2190 and 5232 together. 3,000, I just did that, didn't I? 3,042.5 minus 750 times X minus 2 should equal V. So let's try to plug that in. 3042.5 minus 750, I think I can just use parentheses, X minus 2. Now notice this is the first one that we have where the shear force is not constant. It has X in it as a variable. And so we have the shear force as a function of X, and that is because here the interval that we're in has a distributed load on it. So the distributed load means that we're constantly applying a little bit more force as we move through the interval because the distributed load is spread out over the entire interval. It's not a point load. That's why I erased the lumped version of it that I used when I was calculating the reaction forces. It's because that might get us confused a little bit because it's really a distributed load that gradually gets applied to the beam versus a point load that's applied at a single point. So here we've got our free body diagram for interval, we're on interval 3 now, so, or the third interval. Summation of moments about this cut point. We've got negative, or well, counterclockwise, so negative 2190 has a moment arm of 2.3 plus X. Positive 5232.5 times X as its moment arm. This one, the distributed load, you know, it has this that we got to deal with. So we just found the concentrated value, the total value of this distributed load. It was the 750 times X minus 2. So that's the green, that's what this is. So the units on that would be 750 pounds per foot times X minus 2 feet to calculate the concentrated value of the distributed, the piece of the distributed load, no matter where I cut in interval 3. So that is going to create counter, so that's minus 750 times X minus 2. That's just the lumped value of it, though. I still need the moment arm. The moment arm is going to be X minus 2 divided by 2. So this distance here is X minus 2 over 2. So hopefully that makes sense on how that works. And then minus M, I'm going to move that to the other side of the equal sign so it just says equals M. We could probably type it in this way. It's relatively simple to simplify a little bit, though, at least on the moment side. So we can leave this. We could probably type it in just the way it is, but let's simplify it a little bit. So this would be minus, instead of 750, let's do 750 over 2. So that's 375, isn't it? Make sure. Yeah, 375. And then I've just got x minus 2 times x minus 2, so I could have x minus 2 squared. Although I'm not 100% how to do exponent in MathCAD. Maybe it's the caret. All right, so let's see if we can type this thing in. Not in MathCAD, in WebWork. All right, so negative 2190 times 2.3 plus x plus 5232.5, and that's times x minus 375 times x minus 2, but we need to square that. I think that normally squares things. Yep. All right. So we're almost there. We've almost got the entire set of equations or expressions for the shear and bending moment all through this length of this beam. So let's go back over here and look at the very last section. So the last section would be that little piece. So I would cut through there, draw the free body diagram, do V and M for that piece. This one is not very tricky. Let's go ahead and do it since we're so close. Okay. 2190, 5232.5. We have all of the distributed load. 750, that's pounds per foot. I'm going to write that on there so I don't forget. And then this point load, 1740. And then we have the internal shear force, V, bending moment, M. The reaction at the roller, we cut off of here. It's on the very far end, so we don't need that. Okay. Our dimensions, we have, this is 2.3. This is 2. This is, I don't know, 5.1 it looks like. And then X is that. All right. Summation, or so to find V, summation of forces in the y direction equals 0. Negative 2190 plus 5232.5. Here we could go and, create another lumped load for this whole thing. It was, I erased it, so I don't know what it was. 750 times 5.1, 3825. So it's minus. And then minus the 1740 equals V, so it's plus negative V. And then we moved it to the other side of the equal sign to get it to just be a positive V. So let's see. That's all a constant. Let's just add it together. Negative 2190 plus 5232.5 minus 3825 minus 1740. V is negative 2522.5 pounds. So it's a constant in this section. So V, the shear force, is only a variable. It's only a function of X when it's in an interval that has a distributed load across that interval. All the intervals that do not have distributed loads V is just a constant value for that entire interval. So this one was 25, 22. Negative 25, 22.5. Okay, one more to go. So M is summation of moments about our cut surface from our free body diagram. And we have negative 2190 times, what's it, 2.3 plus x. It's the best way to do that moment. Plus 5232.5 times x for the moment from the reaction at A. Minus 3825. We got to figure out this moment arm. So what's the moment arm from here to there? Got to figure that out. So that would be x. Do we want to do? Yeah, it'll be x minus 7.1. No, that's just is that distance. That's for the other one. So what's the best way? X minus 2 minus 5.1 over 2. Is that what I want? X minus 2 minus that. All right, yeah. So x minus 2 minus 5.1 over 2 is the moment arm for the lumped version of the distributed load. So not quite straightforward, but I guess we can combine the minus 2 and minus 5.1 over 2. So let's see what that is. Minus 2 plus or minus 5.1 over 2. 4.55. So x minus 4.55. Okay. Now we need minus 1740 times x minus 7.1. Not so hard to do that one. And then M is counterclockwise. I said clockwise positive, so I will move it to the other side of the equal sign, and it says equals M. There's probably stuff in there that we can combine together, but let's just write it all out in one thing. All right. So negative 2190 times 2.3 plus x plus 5232.5 times x minus 3825 times x minus 4.55 minus 1740 times x minus, I think it was 7.1. Yep. Let's see if it liked all of that. It did, amazingly. So this is one way. Obviously, it took us an hour. No, because we did that other problem first. But still, it took us a really long time to develop all of these equations, and we didn't really go slow about much of it. I mean, we drew our free body diagrams, and we did our, write out all of our shear or forces in y and our moment equations. So we did all of that, and it took quite a while to do. But now we do have these equations, scattered all in here, that if we wanted to, we could plot those equations and figure out where the maximum bending moment is anywhere in the entire length of the beam. Also do the same thing for the maximum shear force anywhere in the entire length of the beam. And that is a way that you can take a beam like this one and go in and figure out where is it most likely to fail to some sort of flexural bending stress by finding the maximum bending moment and then using that equation from last time, sigma equals negative m times y over I. So using that equation to figure out the worst case flexural stress. But this beam has 2-point loads and a distributed load on it. What if your beam has hundreds of little point loads or all sorts of things like that that you have to break it into many intervals. That could be very time consuming to do. What we're going to do next, we do have time to start this, is we're going to talk about the idea of drawing pictures of this same thing. So it still breaks the beam into intervals between the point loads and distributed loads and all that. But instead of having to write the equation for everything, you can draw a picture following some rules, some if-then statements, kind of like a computer algorithm, and draw a picture of the shear and bending moment based on the same thing that we're doing here, but without having to write the equations out. So shear, I need to angle this a little more so I don't have such a weird angle when I'm writing on it. Shear and bending moment diagrams. Now, a lot of times shear is V, right? So the value of the shear force is V. Internal bending moment is M. So a lot of times you'll see V and M diagrams instead of writing out shear and bending the whole time. All right. So to do this, we need to actually go back to something from last time where we took a beam and we'll do a simply supported beam. It doesn't really matter that it's simply supported or not, but that will be simpler for what we're doing. So we're going to make it simply supported for today. Remember, simply supported means that it has a pin and a roller holding it up. Here, we are going to put all of the loads on here that we might encounter on a beam. Now, I'm going to draw them in a weird way, pointing upwards, but that's just so that some of the stuff we derive later on has positive signs on it because the loads are pointing up. All of this works exactly the same if they were pointing in the normal downward direction, but it just makes a little bit simpler some of our work later in this derivation. So that's why they're pointed up. So we'll put a point load P. We'll put a distributed load. We could put any kind of distributed load on here, you know, any shape we wanted. So it doesn't really matter what the shape is, but it might be simpler to think about it as just this evenly distributed load on there. And then we're going to put, oh, and that's going to have a W for its, I'm going to use all letters. So no numbers here. We're going to make it very generic so that no matter what the numbers are and what the loads are on our truss or on our beam that we're working on, these things still work. Let's call the bending moment, let's call it M. Hopefully that doesn't get confusing with some of the other stuff that we have. And now I want to take a tiny little section. So a tiny little section right in there. I kind of wanted it to move over. It doesn't want to move though. Let's try again. Well, I'll just draw it. There we go. Take this tiny little section and look at just that beam, or just that section of the beam rather. And I'm not going to draw it deformed here. I'm going to draw it as just a rectangle if I can get my pen to behave right. It's kind of acting weird on me. I don't know what's going on with it. Let me see. All right, there we go. I want to draw that section really pretty big. Maybe like that. So this is an enlarged view of the little green box that I drew. So again, it has a point load. It has a concentrated moment. Remember this one is an external moment. So this would be like maybe you have some sort of torque applied to the side of the beam, something like that. You can apply concentrated moments as external loads. So far, we've only been looking at them as these internal bending moments, but you can have them as external moments. Think about you're loosening a bolt or something like that. You're applying a concentrated moment. You're really pushing. You're pushing in one direction on a wrench or whatever. But where the wrench is attached to the nut or the bolt, you're applying a concentrated moment there. So you could have that kind of scenario on a beam. There's some kind of bracket hanging off of it that's twisting it or whatever. And so this is that kind of thing. So this represents some sort of concentrated moment. And then we've got our distributed load. Again, I'm going to draw our distributed load as just a rectangular, evenly distributed load across here. It does not have to be. Just that makes it a little bit simpler to think about. But it does work even if we did not have evenly distributed load all across here. So this really could be any shape you wanted up here, and it would still work just the same. All right. Here, this little tiny section that we're looking at, we're going to call dx or delta x. So it's super tiny. So it's one of those things where I want to do a limit, and I want to send delta x to 0, right? Here, we've already been drawing these things. This is the shear force on the right-hand side. Here's the internal bending moment on the right-hand side. Here's the shear force on the left-hand side of our little section. And here's the bending moment on the left-hand side of our section. All right. So this is that's a W. This is every kind of load that we might have to deal with: a point load, concentrated moment, and some sort of distributed load. It exposes the internal shear and bending moment on both ends of our section. So this is about as generic of a little piece of a beam that's bending as we can get. And it's a tiny sliver, delta x. So what I want to do is the same kind of thing that we were just doing. We were just going and looking at all these intervals in the beam and writing the summation of forces in the y direction had to be in equilibrium. Writing the summation of moments, it had to be in equilibrium also, and developing those interval equations. I'm going to do the same thing here, except I don't have any numbers, so I'm not going to get equations. I'm going to get sets of rules. So summation of forces in the y direction equals 0. All right, so according to this picture, I have VL plus P plus the entire distributed load, so W times delta X. Now, if it's a unevenly distributed load, I would just do whatever type of equation I would need to create that, basically integrate it. So integral of W from one end of the beam to the other end of the beam. I think it does exactly the same thing. I think it's simpler to visualize when it's just an even distributed load. But it does the same type of thing no matter what shape the load is, the distributed load is. Minus VR. All of these concentrated moments, I don't know if I specifically said this last time, but concentrated moments they're not forces, they're moments. So they don't go into any of these force equations. So forces in X or Y or Z never have concentrated moments in them. So these have to equal 0. Okay. I'm going to do something a little bit, not tricky, but it'll kind of be convenient for us. So I'm going to take the shear force, VR, shear force on the right-hand side, and I'm going to redefine it. So I'm going to say that, well, the shear force on the right-hand side equals the shear force on the left-hand side but they may not be the exact same value. You could have change. You know, we did have, where was it? We had this one where the shear force is not constant from one little piece to the next. It does have a changing value. Most of the time it's constant, but there are some places under the distributed loads in particular where the shear force is not constant. So it's not that it equals VL, but it equals the whatever happened before it plus any kind of change in shear. So it could go up or down or stay the same. And when I do that and plug that in for here, I get my equation VL plus P plus W times delta X minus this thing VL plus delta V equals 0. And now I've got positive VL and negative VL. So those just go away. And all I'm left with is the change in shear. So I get P plus W times delta X, VL minus VL, negative delta V equals 0. I'm going to take that delta V and move it to the other side, and I'll end up with delta V. So therefore, delta V equals P plus W times delta X. So this one little equation describes any possible change in shear. So a delta V, it's any kind of change in shear that I can come up with. And the concentrated moments, ML, M, MR, they don't affect this at all. It's just point loads and distributed loads, which is kind of what we saw. Well, we didn't have a concentrated moment on this beam at all, but if we did, we would have still seen that they do not affect the shear. So what I can do is now I can set up, if this is true, you know, if this is true, which there's no reason it's not true, then I can set up some rules. So, for instance, if P does not equal 0, so P, remember, is the point load right here. So P is the point load. So if I'm at a point in the beam where there is a point load, P does not equal 0. So most of the beam, like this one, most all of the beam, there's no point loads, right? There's just these little pieces here and there that there's a point load at. And that's typically true, is that most of the time there's not a point load, you know, on the spot. But if there is a point load, so it's not 0, as delta X goes to 0, so as I get smaller and smaller to only being under the little fibers that are at this point load, delta X going to 0 sends the delta W times essentially 0 is 0, and it says that delta V just equals P. So what this means is that the change in shear, so not the value of the shear force, but the change in shear is a step function of value P. So however much that point load is, that's how much the shear force changes by. So most of the time these are pointing down because they're on the top of the beam. But some of them, the reactions at the pin and the roller, they're usually pointing upwards. So sometimes the shear force shoots straight up because there's a reaction. Sometimes there's a point load applied to the top of the beam pushing down, and it'll immediately drop down. And so this will help us draw a picture of the shear force at any point in a beam. If P does equal 0, so P does equal 0, now I've got my equation saying delta V equals W delta X. So W was the idea of this distributed load. So whatever the function W of X looks like, for me it was just a constant evenly distributed load, but it could be some oddball function. I could rearrange this thing and say that, well, delta V over delta X equals W. And delta V over W, or delta V over delta X is, remember, X is our horizontal axis, V is the shear force. So this term is just a slope, right? dV over dx. So it's a slope equal to whatever W is. So in our beam up here, W was 750 pounds per foot. Technically, it's negative 750 pounds per foot because the point load, or the distributed load, is pointing downwards. But that tells me the slope of the shear force diagram that I'm trying to draw is that value. And this part of the equation tells me that the total change in shear, so delta V, equals the area, the area being a force of the distributed load, so the lumped value of the distributed load. And that's really all of the equations I need to draw the shear diagram, because there's nothing else going on in this equation. I've got P, I've got W, and that's it. Delta V, delta X. So what this would look like is, let's take the one that we just worked on. Let's take this guy. Let's copy. How are we going to copy this? Let's do it. Let's actually go back to WebWork and copy it over there. Copy that one. Okay. I guess we didn't get we actually need our values on here. So 2190. I'm gonna cheat again and just color over these instead of redrawing everything. This one was 5232. I've kind of forgotten everything now. 5232.5. 750 pounds per foot. 1740 pounds, I believe. And then I don't know what BY was. We didn't use that one. 2522.5. So we also needed our dimensions. So let's see, we had 2.3, 2, 5.1, and 2.7. Okay. All right. So we can, how you do this is, normally you draw your free body diagram of your beam that you're dealing with. So this is our beam. Then you put it at the top of a area that you're going to draw this shear and bending diagram, because these are long rectangular like diagrams with the beam at the top and then the shear force underneath that and the bending moment underneath that. So I would go in and draw some guidelines. So let's just draw them in green. So there, we're only drawing the shear diagram right now, so we don't need that much space. Normally you're drawing the shear and the bending, but we haven't written our rules for the bending yet. Okay, so you just draw you some guidelines showing where the different things happen. So I drew one everywhere there was a point load or the start of a distributed load, or if we had a concentrated moment, then where that was also. Then we need a baseline, so we're just going to draw a horizontal line somewhere. And that is our shear equals 0 pounds, right there. And you start left to right on the beam, and you follow these rules. So if there is a point load, then you change the shear by the magnitude of that point load. And that's what exactly happens at the very beginning. Is there's a point load. I start at 0 shear, and immediately there's a negative 2,190. So I would drop down 2,190. I'm at 0, so I go down to negative 2,190. Let's just say that this is 1,000, this is 2,000. So negative 2,190 is like right there. So there's my dropping down immediately, my step change in shear. I guess I technically have one other rule that I didn't write down. Let me see if we can make some room for, how can I may have to like move all of this. All right, so technically I have one other rule that if P equals 0 and W equals 0, so there's no point load, no distributed load, then my equation just says that delta V equals 0, because the entire right-hand side of my equation up here that's in yellow is just 0. So there's no change in shear. So it's not that the shear force equals 0, there's no change in it. And that's what happens next in our diagram here. I'm down at negative 2,190. So from that point to the point where the, I think that was the roller at A, there's nothing going on. There's no point load, there's no distributed load in this section, nothing happening. So there's no change in shear. So it just stays constant. And then I encounter that positive is pointing upwards, 5,232.5. So I'm at, again, low battery. All right, I'm at negative 2,190. I encounter a positive, so plus 5,232.5. And I immediately step change from negative 2,190 to 3,042. So right in here. So I do that. And then there's no change until I encounter the distributed load. Now the distributed load doesn't give me a step change. What it does is there's a slope, a gradual change. And that gradual change is however severe the distributed load is. How, in this case it's 750 pounds per foot pointing down. Again, it could be any function. Mine are just going to be nice, evenly distributed loads, but it could be any function. And the entire, by the time I've gotten to the end of the distributed load, I have lost, in this case, what was it, 750 times 5.1, I've lost 3,825. I'm at 3,042.5, so 3,042.5. If by the end of the distributed load I have lost, so minus 3,825, I'm down at negative 782.5. So there's this gradual change like that. And the slope of this line equals negative 750 pounds per foot. And that's what this is telling me right here, is that's how I calculate the slope of it. Okay. So now I'm at negative 780. Was that 82 or 87? 82. That's a 2.5. And then don't forget this point load. So minus, it's pointing down, 1740. Oh, well, minus 1740 and the 782.5 I'm already at. I go down again, and I go down to about right here. Oh. Things are kind of hanging up on me. Here. Negative, so 782.5, negative 782.5 plus negative 1740 is negative 2522.5. Step change. Nothing happens in this little interval. I encounter this guy, which happens to be a positive 2522.5. I'm at negative 2522.5. So I get right back to 0. And so this is a picture of the shear force anywhere in this beam. And, you know, it took us a while to draw it and all. But it is quite a bit faster than trying to figure out an interval equation for every interval in the beam. Once you're not having to talk your way through it. And so I can quickly see that the worst case for shear was in that second interval. You know, here's our maximum shear. And again, shear doesn't matter positive or negative signs, but the absolute value is highest right here. So now I know that in this interval, from x equals 0 to x equals 2 feet, that's the most likely place for a shear failure because it has the highest shear force. Now, it's still not a probably high enough force to actually shear the beam, but it is where the shear is maximum. One other thing I need to do about this, we won't be able to do the bending moment part today. We'll do that on Monday. But one other thing we can do with this is it's going to be important to know this distance. Because when we do the bending moment, what we actually do is we calculate the area of this diagram, the shear diagram, in order to figure out the moment. So basically you're integrating the shear diagram and putting in any concentrated moments that you have. In this case, we don't have any. And so in order to integrate this, I need to know the size of this triangle right here. And so I take this value, we'll call it x. X is going to equal the height of the triangle, which is 3042.5, that's pounds. And divide by the slope. Now, I don't have to actually put a negative sign on the slope. And this will give me how many feet. The pounds cancel out, I'll have feet. It'll give me how many feet it takes to get from here to where it crosses the shear equals 0 axis. So 42.5 divided by 750 is 4.06 feet. So that's almost, remember that's a 5.1 foot long section. So there's this little guy, x2, I guess this is x1. x2 would just be, in this case, 5.1 feet minus x1, 1.04 feet. So that'll be useful for the next step when we do the bending moment diagram drawing. We just don't have time. There's enough time to do a little bit, but I don't think there's not enough time to finish everything that would need to be done for doing the bending moment diagram. So on Monday, we'll pick up with this diagram, but instead of writing summation of forces in the y direction, we'll write summation of moments about this center point, and that will let the moment ML, MR, and EM, it'll let those enter into the equation, and suddenly we can write the similar set of if-then rules for the moment. There just isn't going to be time to do all of that and doing a sample with it, so we'll do that on Monday. All right. I don't see any other questions in the chat over there, so I think we must be good there. I have opened up homework 12 in web work, which is a little bit of the stuff that we did with the beam. I think it has some of these style problems in it, I think. And keep working on those frames. They're not as, most of what we do from here forward, unless you ask a particular question to be solved about frames, is going to look more like just a beam. So more like one of these with maybe a shear and bending diagram or calculating a beam stress. So it won't necessarily look like a frame. So if you're still having trouble with frames, ask some specific questions and we can work another one. Oh, you know what? Yeah, that's a good point. Monday's a holiday, so we're not actually going to be on Monday. It will be Wednesday. I didn't even think about that. But yeah, Monday is actually a holiday, so we won't be until Wednesday. We'll come back and do the moment. What that'll let us do, though, is it'll let us set up the moment equation, and then we can work one from start to finish, doing all the flexural stress, the shear and bending diagram. It'll do the whole thing. It'll take the whole class to do that once we get there. So that'll let us do all of one of those and finish up this shear and bending diagram. So no class on Monday. All right. I will see you guys on Wednesday, not Monday.